So as we know that in the reaction turbine, only the part of the total head is converted into the kinetic head before it reaches the runner, and water completely fills the passage, all the passage in the runner. So the pressure of water changes gradually as it passes through the runner. So more commonly used type of reaction turbines are the Francis turbine and the Kaplan turbine. I had already discussed about the Kaplan turbine in my previous lectures. So today I will be concentrating only on Francis turbine. So in Francis turbine, the water enters the runner radially at its outer circumference and moves towards the inner circumference. So this is the component parts of uh, the reaction turbine, where so water is brought from the penstock. From the penstock it enters the scroll casing, or also called the spiral casing, and from there it enters the speed ring or the steering. The speed ring or steering consists of an upper and lower ring, which is connected by the stay vanes, and from the stay vane water is directed to the guide vanes. So generally the guide vanes are used to regulate the water to the runner vanes at an appropriate angle, which is according to the design. So it sends the water at an angle alpha, and here the runner consists of a series of runner vanes, generally varies from 16 to 20 to 24. Here the water enters at the outer circumference and moves radially inwards to the inner circumference. So now, as I told you, the penstock will enter the scroll casing, which is also called as the spiral casing, and this spiral casing is completely surrounding which surrounds the runner. So what is the purpose of the casing? The purpose of the casing is to provide even distribution of water around the circumference of the turbine runner. Thus, it maintains a constant velocity for the water so distributed. So in order to keep the velocity of water constant throughout the path of its runner, the cross-sectional area of the casing is gradually decreased. Now, as I told you, from the scroll casing or a spiral casing, the water passes through the speed ring or a steering. So here the speed ring consists of an upper ring as well as a lower ring, which are held together by a series of fixed vanes, or also called the stay vanes. So you know that speed ring or a speed ring has two functions. That means it directs water from the scroll casings to the guide vanes, and also it resists the load that is imposed upon it by the internal pressure of water. Also, it also takes up the weight of the turbine and electrical generator, and transmits the same to the foundations. So now from the water that is coming with the scroll casing goes to the steering, and from the steering or speed ring, the water passes through series of guide vanes which are provided around the periphery of the turbine runner. So the function of the guide vane is to regulate the quantity of water supplied to the runner, and also it will direct the water at an appropriate angle alpha. So now the runner of a Francis turbine consists of series of curved vanes or runner vanes, which is evenly arranged around the circumference. So the vanes are so shaped that the water enters the runner radially at the outer circumference and leaves the runner at the inner circumference. Here, water after passing through the runner flows to the tail race through a tube known as a draft tube. So this draft tube is a pipe or a passage of gradually increasing cross-sectional area which connects the runner exit to the tail race. So here the end of the draft tube is always dipped in water, or submerged below the level of water in the tail race. As to coming on the work done, uh, it is same as what with the concept that we had already studied in impact of jets. The same velocity triangles are written here, but only thing is here the little bit you have to understand about the center of rotation. So the distance from the center of rotation to the outlet, and distance to the from the center of rotation to the inlet is quite different. So that's the reason why d is greater than d1. So therefore distance to the inlet is always greater than distance to the outlet. So therefore d is greater than d1. Hence the tangential velocity at the inlet will be always greater than the tangential velocity at the outlet. So as you know that here, if I draw a tangent to the wheel here and draw a perpendicular, it will come somewhere here. So similarly, if I draw a tangent at the outlet tip and draw right angles to the tangent, it will come and meet at center O. So this is called the center of rotation. So now the distance here is, say it is like R1, so therefore corresponding diameter is D1. Similarly the distance is R, so therefore the corresponding diameter is D. So here D is greater than D1. So now here uh, here the jet will the water will come and strike the vane so at an angle alpha. So this will be sent by the guide vanes. So therefore by the time it strikes, the vane would have moved with velocity u. So therefore it strikes with velocity vr and moves out in the tangential direction. So the component of v in the radial direction is vf, component of v in the horizontal direction is vw. Similarly theta is known as angle of vane at the inlet. So now here after it glides, then it comes out with velocity vr1 in the tangential direction, and therefore by the time it comes out, then the vane would have moved with velocity u1, and then the line joining from tail to tip is absolute velocity v1. The component of v1 in the radial direction is vf, that is vf1 we have to write vf1, and the component of v1 in the horizontal direction is vw1. So this angle phi is known as the vane angle at the outlet. So this is the diagram that you have to follow while solving the problems. In this case, the angular momentum principle is used. So it's that the torque exerted is equal to rate of change of angular momentum. So angular momentum is defined as moment of momentum. So here mass per second can be written as mass per second, that is density into volume per second. So density into discharge, so density discharge is area into velocity. So therefore mass per second is nothing but rho av. So what is angular momentum at the inlet? So now momentum is mass into velocity, so therefore mass into velocity. So there is angular momentum is moment of momentum, so taking distance r, so you give it will give momentum. So therefore mass into velocity into the distance will give moment of momentum, which is nothing but angular momentum. Now angular momentum at the outlet can also be calculated like rho av. So here it is here it is minus vw1, because it is in the opposite direction of this. So therefore distance is r1. Why we take vw, velocity of whirl? Because the perpendicular distance to vw is r, and that's the reason why we take to take moment of momentum, we take the component vw. So here also the component minus vw1 is taken. So now applying according to the angular momentum principle, you can find out what is the torque exerted. So torque exerted is nothing but rate of change of angular momentum. So change is for the minus is for the change. So therefore rho av vwr minus, here minus of minus will become plus. So rho av is common term. So you can write it as vwr plus vw1 r1. Now you can say that when work done per, what is work done per second? Work done per second is nothing but torque into angular velocity. So let the angular velocity be omega. So now omega, bring it inside. So omega into r is nothing but u. Similarly, omega into r1 is nothing but u1. So therefore, with the formula becomes rho av vwu plus vw1 u1. So depending upon the velocity triangle, so we can have in general we can write plus or minus vwu plus or minus vw1 u1. So depending, so if beta is less than 90 degree, use plus sign. If beta is greater than 90 degree, use minus sign. If beta is equal to 90 degree, vw1 will be 0. So now you know that this is the output of the output. So similarly input is nothing but omega qh. So therefore hydraulic efficiency can be calculated, which is output by input. Also overall efficiency is shaft power divided by the water power. There are few terms which are associated with the problem, what is the ratio of width of the wheel to the diameter of the runner is always represented as n, and it generally varies from 0.1 to 0.45. Sometimes flow ratio will be given. The flow ratio is Vf by root 2 gh. It varies from 0.15 to 0.3. Similarly, speed ratio is also given, which is u by root 2 gh. So therefore, it varies from 0.6 to 0.9. Now coming to the problem, inward flow reaction turbine works under a head of 20 meters, so h is 20 meters. It makes 380 rpm, so n is 380 rpm. The outer diameter of the runner is 60. So here outer diameter is at the inlet. So therefore D is 0.6, whereas D1 is 0.3. Velocity of flow entering the runner, that is V, is 13 meter per second, and the angle it makes, that is alpha, is 10 degree. So we have to assume radial velocity of flow to be constant. That means Vf should be equal to Vf1 should be equal to constant, and let the water leave in the radial direction. So water leaves in the radial direction, so discharge is radial here. So beta is always 90 degrees. So Vw1 will be 0. So you have to determine vane angles at inlet and outlet, and also determine hydraulic efficiency. So now given h, which is 20 meters, n is 380 rpm, so d is given 0.6, d1 is 0.3, so velocity of flow is constant. So therefore we have v, which is given 13 meter per second, alpha is 10 degrees. So now they have given that radial discharge at outlet, so beta is 90 degrees, so Vw1 will be equal to 0. So now knowing d and n, we can find out u and u1. So therefore u is pi dn by 60, so which is 3.14 into 0.6 into 380 divided by 6 comes to 11.93 meter per second. Similarly, the initial velocity at the outlet can be determined like pi d1 n by 60, which comes to 3.14 into 0.3 into 380 by 60, which comes to 5.97 meter per second. Now because alpha is known, v is known, we can find vf and vw. So what is vf? It is v sine alpha. So using this triangle, so it is v sine alpha, whereas vw is v cos alpha. So that gives vf as 2.26 meter per second and vw as 12.8 meter per second. So now we know vw, we know u, and we know vf. So hence tan theta is nothing but vf by vw minus u, only this. So therefore theta can be calculated. That is what asks the vane angle at the inlet. So that's how we find out. Substitute the value of vf, substitute the value of vw and u, so we'll get theta 68.95. Now it is said that discharge is radial at the outlet, so therefore it moves out in at 90 degree. So therefore this is in the tangential direction Vr1. By the time it comes out, the velocity will be u1, velocity of the wave. So therefore it comes out at 90 degree. So here, since it comes out at 90 degrees, so Vw1 will be equal to 0. So V1 has to be equal to Vf1, and since it is given that velocity of flow is a constant, should be equal to Vf. So here it is required to find the angle phi, so we can make use of this triangle because we know u1 and we know vf. So what is tan phi? It is vf1 by u1, which so that where vf1 is known and u1 is known, so hence phi can be calculated. So we also know that hydraulic efficiency is the work done per second by water power. So therefore rho AB VWU. So here VW1 is 0, so this goes off. So AV and Q, that they get cancelled out. So this is specific weight can be written as rho G. So rho gets cancelled. So hence you can remember that it is VWU divided by GH. So knowing VW, knowing U, GH, so we can calculate hydraulic efficiency, which comes to 77.83%. So this is how you solve the problem. So it's similar to the problems that we had already discussed, except that all the problems are similar, but here U and U1 are quite different, and also there are a few terms associated with the efficiency that we have to note down here. Now it is given that an inward radial flow turbine is required to operate under a head of 10 meters. A small model has been constructed and then it works under a head of 10 meters. The speed is say 175 rpm to develop 150 kilowatts. So you have to determine the diameter of the runner at the inlet and outlet. So also discharge, guide vane angle, that is alpha, runner vane angles theta and phi. So here the outlet diameter is given as 0.66 times the inlet diameter. Okay, so that means d1 is 0.66 times the inlet diameter is at the inlet, so that is d. So the inlet peripheral speed means u is 0.75 root 2 gh. So velocity of flow is constant, which is vf equals vf1 equals 0.16 root 2 gh. Discharge is radial again, so vw1 is 0, beta is 90 degree. So then hydraulic efficiency is given, oral efficiency is given. We should also calculate width of the runner, that is b and b1. So that is how go ahead. So now so since the here it is given that d1 is 0.66 times d. Okay, so now since this expression was given, the u is 0.75 root 2 g, h is given, so we can calculate u 10.51 meter per second. Similarly, velocity of flow was a constant, so therefore vf should be equal to vf1 should be equal to 0.16 root 2 gh, that comes to 2.24. Now we know overall efficiency, hence overall efficiency is P by WQH. So therefore P has to be converted, so that is 150 kilowatts to be converted to watts, multiplying by 1000. So you know overall efficiency, you know specific weight 9810. So Q into H is 10, so Q can be calculated. So Q is 1.88 meter cube per second. Now you know that discharge is radial at the outlet, so beta is 90 degrees, so VW1 will be 0. So that gives the formula hydraulic efficiency as VWU by GH. So from this you can calculate hydraulic efficiency, which is 0.86. So VW has to be calculated. So U is known and H is known. So VW can be calculated, which is 8.03 meter per second. And now from knowing U, which is 10.51, we can calculate the diameter which is asked. So therefore 10.51 should be equal to 3.14 D into N is 175. So D comes out to be 1.15 meters. Similarly, the D1 can also be calculated at the outlet, which is 0.66 times D, so which is 0.76 meters. Since you know D1, you can also calculate U1, which is pi D1 N by 60, which is 6.96 meter per second. So first thing is that here we know that U is around 10.51. Okay. And also the VW is calculated, so VW comes to about 8.0. Here in this case specifically U is greater than VW. So now you know that V is this, so U starts from here, but since U is greater, it will cross this line and come towards here. So but the earlier cases and all the problems we solved was somewhere U would stop here, that U was always less than VW. So therefore this was VR and the angle theta was this. So but in this case the angle theta will be obtuse here. So now what you have to do is that if you know velocity V, take the component Vf and Vw. So therefore you know tan alpha is equal to Vf by Vw by this triangle. So now you can calculate alpha 15.6, and now using this tan theta dash is Vf by U minus Vw1. Earlier we used to write Vw minus U, since U is greater than Vw, so we write as U minus Vw. So that gives theta dash, hence theta can be calculated as 137, which is an obtuse angle. And also since discharge is radial, you know that it comes out at 90 degrees. So therefore this is VR1. So the angle phi can be calculated, which is VF1 by U1. So knowing VF1, which is equal to VF, and you also know U1, so phi can be calculated. Okay, so we also have what is known as the discharge formula. So discharge formula is, as we have used in the centrifugal pump, the same formulas can be used. So at this K pi B into D is nothing but the area. Since it is a radial velocity flow, so VF is in the radial direction, so VF is taken as the velocity. So therefore area into velocity gives the discharge. So K is the factor which accounts for the thickness of the veins. So therefore if 6% of the area is blocked by the veins, then we write K as 0.94. If 8% is blocked, then we write K as 0.92. If 10% of the area is blocked, then we write it as 0.9. So here nothing is mentioned about that, so therefore we can take K is equal to 1. So B is the width of the wheel or the runner, and D is the diameter, so velocity of the flow, hence the B can be calculated. Similarly the same discharge has to pass even at the outlet. So here the corresponding width and corresponding diameters are taken, so therefore, and corresponding velocity of flow, so therefore you can calculate B1. So and this is more important problem where the external and internal diameter of an inward reaction flow turbine is given, so therefore D is 1 meter. Similarly D1 is 0.5 meters. Veins are radial at inlet, so this is very important statement. So when I say that veins are radial at inlet, so that means that VR will because it was issuing at an angle theta which was less than 90 degree, but when they say that veins are radial, so radial means that VR will be in the radial direction. So that means whatever the direction of VF will be the direction of VR. So therefore theta has to become 90 degrees. When theta is 90 degrees, then VR will be equal to VF. Okay, so because the component of V in the radial direction is Vf, so that has to be equal to Vr. So but you know that, so this is U, so that is because the horizontal component of V is Vw, so U has to be equal to Vw. So this is what you find out in whenever the vanes are radial. So it is only specific related problems where when vanes are radial, then Vw is 0, then Vr will be equal to Vf. But since Vf is given here, so therefore Vr is known here. So now you can use this because the angle alpha is given. So tan 10 degrees is Vf, which is 3. You can find out U. So therefore the U can be calculated. Okay, U can be calculated here. So using U, and since D, so N can be known. So this is how. So unless you write this diagram, then you cannot solve this problem. So therefore you have to know that. So it is a right angled triangle whenever the vanes are radial at inlet. So using U is equal to pi d n by 60, then you know U, so you know D, so n can be calculated, which is 325 rpm. So similarly, you knowing n, you can calculate U1, which is pi d1 n by 60, so therefore 8.504 meter per second. Now it's also said that discharge is radial at the outlet. When the discharge is radial at the outlet, beta is 90. Again, it is a right angle triangle. So here this will be in the right here at beta is equal to 90 degrees. So V1 will be equal to Vf1, which is constant. Again, it should be equal to Vf, and this is U1. So tan phi is Vf1 by U1, which is Vf1 is known, U1 is known, hence phi can be calculated. So this is the problem. So coming to the next problem, the inward reaction flow turbine has internal diameter of 1 meter. So D is 1 meter, D1 is 0.5. Turbine is running at 200 rpm, so N is 200 rpm. So width of the turbine at inlet, so B is 0.2 meters. Velocity of flow is constant, so Vf1 equals Vf equals 2 meter per second, and angle, guide blade angle means alpha 10 degrees. Discharge is only radial at outlet, so therefore Vw1 is 0, so beta is 90 degree. So then you have to find vane angles, that turn phi, you have to find discharge, you have to find power developments, work done per second, and hydraulic efficiency. So here knowing D and N, we can always calculate U, so which comes to 10.47 meter per second, and also you can, knowing D1 and N, you can calculate U1, which is 5.23 meter per second. Now using this diagram, so therefore you know that U here, okay, so you have, so tan alpha is Vf by Vw, taking this triangle tan because the component of V is Vw and Vf, and this is angle alpha, so hence you can find out Vw. So now you can observe that here U, which is 10.47, is less than Vw, so therefore it stops here only. We had a diagram where in the previous problem where U was greater, so theta was obtuse angle, but in this case, since U is less than Vw, we get theta as an acute angle. Okay, so therefore tan theta can be written as Vf by U minus Vw, whereas in the other case it was sorry, Vw minus U. In the other case it was U minus Vw. So in this case tan theta is nothing but Vf by Vw minus U. So therefore we get theta 66.5, which is less than 18 and is less than 90 degrees. Okay, less than 90 degrees. In the earlier case it was obtuse angle. Now discharge is radial, so it leaves at 90 degree, so therefore tan phi is which is Vf1 by U1, hence phi can be calculated. So now knowing all this quantity Vf, which is here B and D, you can always calculate discharge from the formula area into velocity K pi B into D. Nothing is mentioned about the area block by area which is blocked by the base, so therefore K is taken as 1. So here knowing B, which is 0.2, D, which is okay 1, and velocity of flow as 2, we get discharge as 1.26 meter cube per. Now you can calculate work done per second, since discharge radial Vw1 will be 0. So that gives A into V is Q, so Vw into U, so that 1000 into Q 1.26, Vw is known and U is known, so therefore dividing by 1000 we get 149 kilowatts. Now since the hydraulic efficiency is not given, we are not able to find out the net yet. In the case of a lack of data, we can use this formula, that is H minus V1 square by 2G should be equal to Vw into U, or H is equal to Vwu. So that means this is nothing but Vwu by G. Okay, that is plus V1 square by 2G. So this can be always written only you can use it in the case of lack of data to calculate the net head. So therefore here h can be calculated by, because knowing vw and u, and here v1 is equal to vf1, so that is nothing but 2. So therefore substitute v1 as 2 square here divided by 2 into 9.81, so that gives 12.31. so this formula cannot be used in all the problems. If there is no other data to find out this head, then only we can use this formula. Okay, so everything is in terms of head units. So VWU by G is in terms of head units. So this is also in the head units. So therefore this is nothing but the net head. So net head should be equal to, that is input should be equal to the output, so which is 12.31. so make use of in the hydraulic efficiency as VWU by GH. So unless you find out H, you cannot find out hydraulic efficiency. So that's the reason why we have used this formula to calculate the net head. So that comes to 98.32%. So next problem is that we have inward reaction flow turbine which has an external diameter of 1 meter, internal diameter of 0.5 meters. Then we have hydraulic efficiency 90%. The head is given at 36 meter. Velocity of flow at outlet is given, and which is Vf1. It is not constant here. Discharge at the outlet is radial. Vane angle at outlet is 15° phi. Width of the wheel at the inlet as well as the outlet. So B is equal to B1, which is 100 millimeters is given. We have to find alpha, we have to find N, we have to find vane angle at inlet, that is theta, we have to find discharge and the power developed. So now, so coming to this, we have, because it is given that discharge radial at the outlet, we can write this diagram. So V1 should be equal to Vf1, beta is 90°. So this is U1, this is VR1. So therefore phi, from phi, because phi is given as 15 degrees, so we can make use of this, and also we can make use of Vf1. So here tan 15 is equal to 2.5 by U1, so U1 can be calculated. So knowing U1, which is pi d1 n by 60, so you can calculate the speed. So therefore the speed is calculated, which is 356 rpm. Now knowing speed, you can calculate tangential velocity, that is u pi dn by 60, so it comes to 18.66 meter per second. Now you can make use of hydraulic efficiency. Since discharge radial, we can write VWU by GH. So knowing hydraulic efficiency, knowing u, knowing h and g, so we can calculate VW. So in this case, you can observe that here u is greater than VW, so therefore this is u, so VW stops here only, so therefore theta is obtuse angle. So you can also, because to calculate this we need, V is not given, so hence we need Vf. So for calculating Vf, we can make use of discharge at the inlet should be called discharge at the outlet. So therefore, since we know K, we know pi, we know B, because B and B1 are same, D is 1, D1 is 0.5. Velocity of flow at the outlet is given, so that will give velocity of flow at the inlet by this. Okay, so everything cancels, so we get 1.25 meter per second. Now you can make use of tan alpha is Vf by Vw, so which gives alpha as 4.2. So making use of this triangle, tan theta dash is Vf by u minus Vw, so that gives theta dash, hence theta can be calculated. So now the discharge also can be calculated as K pi Bd Vf, so where the B is known, D is known, Vf is known, which is 1.25, hence gives 0.3925 meter cube per second. And hence work done per second can be calculated. Here VW is known and U is known, so A into V is discharge. So after calculating discharge, you can substitute here and get work done per second in watts. Divide by 1000, you will get in kilowatts. So this is the last problem for the inward reaction flow turbine, which rotates at 370 rpm. So N is 370 rpm. So wheel vanes are radial at inlet. So wheel vanes are radial at inlet. So this is one again specific problem where theta is equal to 90 degrees. So inner diameter of wheel is half, that is at the outlet, half of the outlet diameter. So there Yeah, that means D1 is zero point 0.5 times D. D1 is zero point 0.5 times D. Velocity of flow is constant, so Vf should be equal to Vf1 equal to 2 meter per second. Water enters the wheel, that means alpha is 10 degree 4 minutes, so 10 plus 4 by 60. So at the inlet, so therefore, and then the width of the wheel at the inlet, so B is 75.075. Area of flow blocked by the vane is 5. So K factor comes here, which is 0.95. You have to find what is the net available head, wheel vane, that is theta, D and D1, and power developed. Okay, now here it is a right angled triangle at the inlet, which is, since the vanes are radial, so therefore theta is 90 degree, so hence this VR has to be in the radial direction, which is velocity of flow VF, because the component of V, horizontal component is VW, which is also equal to U. Okay, so therefore now tan alpha is VF by U. So now since VF is known, which is 2, then alpha is known 10.067, so u can be calculated. So using u, you can calculate d, because u is pi dn by 60. Knowing n, knowing u, so we can calculate d, and d1 is zero point 0.5 times, okay, d, so therefore 0.291, and hence knowing d1 we can calculate u1. But here in this case, what is vw? So unless you write right angle triangle, so then only you will get vw should be equal to u. So since already u is calculated, so vw is also 11.27. Now say there is no other formula to calculate net rate, so therefore we are using this formula, which is VWU by G plus V1 square by 2G, because VW and U is known, and V1 is nothing but VF1, that is equal to VF, which is 2, so therefore you can calculate the net head as 13.15. Now using this triangle, so tan phi is Vf1 by U1, so therefore phi can be calculated. Hence discharge is given by the formula area into velocity. So that is K is here, see here, it is not 1, yes, because 5% is blocked, so K is 0.95 into 3.14, B is 0.075, diameter is given, which is calculated 0.582, and velocity of flow is known as is 2. So therefore discharge is 0.26. Hence power developed or work done per second can be calculated as rho AB VW, taking discharge as radial. So therefore the power can be calculated.